Gaia's main objective is to determine the positions, motions, and distances of billions of stars. When the images of the stars from Gaia's telescopes move across the focal plane, their positions at a given time are determined by the light-sensitive astrometric CCDs. Subsequently, the light from the star passes through prisms, producing low-resolution spectra, helping us to determine, for example, the temperature of the stars. Finally, the diffraction grating and carefully crafted lenses in the radial velocity spectrograph disperse the light into high-resolution spectra, allowing us to determine the speed of the stars along the line of sight and their chemical composition. This animation presents some of these stellar spectra where the brightness of the stars is shown as a function of wavelength. The variations are due to the light absorption from atoms and molecules present in the stellar atmosphere. Most of the ordinary matter in the universe consists of the lightest elements, hydrogen or helium, created during the Big Bang. For all heavier elements, such as calcium and iron, astronomers use the word metals. Most of these metals were created by nuclear fusion in stars and given back to the interstellar medium, for example, by stellar winds and supernova explosions. In this way, our Milky Way is enriched in metals over the course of time. Here we are using the metal abundances derived from the RVS to colour the stars. Blue represents a low metallicity, red a high one. Green lies in between. The stars shown here are those for which the chemical compositions could be determined with the RVS spectrograph. Older stars should contain only a small amount of metals, while stars born later should have a higher metallicity. We now travel thousands of light years towards the centre of our Milky Way and observe stars with very different amounts of metals in their atmospheres. Now we fly out of the plane of our galaxy and look down on the Milky Way from above. In order to see all of the stars of our sample, we enhance their brightness and move closer to them. The distribution of metals shown here results from the mixture of stars of different luminosities. Gaia can detect dwarf stars with very low luminosities only if they're very close to us. Therefore, we now select only the very luminous giant stars in our sample, which can be detected by Gaia even at a distance of several thousand light years. We see that the enrichment in metals decreases as we move from the galactic centre to the outer galactic regions. This informs us about the chemical composition of the gas from which these stars were formed over more than 12 billion years of galactic history. Therefore, and thanks to the high level of detail of these Gaia observations, we can infer the rate at which the stars were born, the arrival of gas from the intergalactic regions, and the migration of stars inside the disk. The next sample consists of very young stars, only a few 100 million years old, and therefore about 4 billion years younger than our Sun. They are located along curves that reveal the spiral arms of the Milky Way where these stars were formed. The Sun is in a region outside the spiral arms. We see again the decrease in the metal enrichment as we look further outwards in our galaxy. This is the largest sample of young stars for which we have a detailed chemical description, thanks to Gaia Data Release 3. Because there are fewer of the young stars, we can show more of them individually. This allows us to visualize the motion of the stars as measured by Gaia. This short sequence corresponds to 5 million years. We see that the stars move together, illustrating the stellar motions in the disk of our Milky Way. Let us now move to the plane of our Milky Way and see our galaxy edge on. First, we look again at our full sample of stars for which the chemical compositions could be determined by Gaia Data Release 3. In the following, we will split this sample into the same groups as before. Now we show the sample of giant stars edge on. These luminous stars allow us to determine the chemical profile of the Milky Way disk, including its older stellar populations, far from the galactic plane. As we move outwards from the galactic center, the disk density and apparent thickness decreases, like the chemical enrichment. In addition, in the inner regions, the stars near the galactic plane are more enriched in metals than the older stars, at higher distances above and below the plane. This is the sample of young stars, shown from the side. The stars in the spiral arms are located in the so-called thin disk, which has gas and ongoing star formation, and to which our Sun belongs. This thin disk profile becomes thicker as we move outwards from the galactic center. Again, we show how these stars will move during the next 5 million years. We can see the disk rotation, with the stars approaching in our direction. Up to now, we have shown the overall global enrichment in chemical species in the atmospheres of the stars. However, we have also determined individual abundances of chemical elements. As an example, we color-code here the amount of calcium in the young stars, an element which is, for instance, important for the stability of our bones. Finally, we show a group of stars that has no strong concentration towards the galactic plane. Almost all of them are very poor in metals, and therefore shown as blue in this video. The stars were identified by their peculiar motion and chemical composition. They are the remains of a dwarf galaxy, called Gaia Enceladus, that merged with our Milky Way about 8 to 11 billion years ago. These stars illustrate that the galaxy in which we live is an ever-changing system, formed thanks to the assembly of stars and gas of different origins.